Hello guys, hope you all are doing well. So in the continuation of the previous grade series, we are solving the questions of grade 1990. So today we have a new question, and this is from plant design and economics. So for plant design and economics, we have Peter Max Timberhouse. Okay, so this is a very good book. Okay, so we'll see the question. Find the dimension of hollow cylinder. Okay, radius and height. With both and closed, which can hold volume 27 pi by 4 meter cube of water and has a minimum outer surface area. Okay, so suppose we have a cylinder. Okay, so this is our cylinder. So we have to minimize the total surface area. So surface area is equal to total surface area, curved surface area of cylinder plus upper end and lower end. So 2 into pi r square. Okay, now we have volume 27 pi by 4. Okay, वॉल्यूम इज गिवन बाय पाई आर स्क्वायर एच. पाई पाई का हिसाब कर देते हैं. ओके, सो एच इज इक्वल टू 27 by 4 r square. Okay, putting this value here, so surface area is equal to curved surface area is 2 pi r. L and height is same, so into 27 by 4 r square plus 2 pi r square. Okay, we can so pi 27 by 2 2 2 is 4. 27 by 2 pi upon 27 by 2 pi upon r plus 2 pi r square is equal to surface area. Now dy of dr is equal to 27 by 2 pi d by dr of r into minus 1 upon r square plus 4 pi r. Okay, which is equal to 0 for minimum surface area. So it will give minus 10 minus 27 by 2 pi upon r square is equal to minus 4 pi r. So pi and pi cancel, minus and minus will cancel. So 27 by 4 to 8 is equal to r cube. So r is equal to 3 by 2. Since r is 3 by 2, okay, we will calculate h. Way from where? From here. Way from here. H is equal to 27 by 3 to 3 into 2. 3 3. Okay, so this is the question. So switching over to the next question. 1000 kg per hour of an aqueous solution of 20% Na2CO3 is cooled gradually to T degree Celsius to crystallize out Na2CO3 dot 10H2O. Okay, so wait, first we will make a diagram. So if this is our crystallizer, this is our crystallizer. Okay, crystallizer. Okay, and at T is equal to T degree Celsius, that means this temperature will be less than the feed temperature. T is greater than T. Okay, and in feed it is coming 1000 kg per hour of 20% Na2CO3 solution. ठीक है. Now it will give crystals, okay, and solution. ठीक है. Assuming no loss of Na2CO3 through the mother liquor adhering to the crystals and no carryover of the crystal with the mother liquor. Draw neat block diagram showing the inlet and exit composition flow rate. Okay, molecular weight of Na2CO3 can be assumed 106 in water 80. Okay, calculate the percentage of Na2CO3 recovered in the form of crystal. Okay, so let this stream be A. ठीक है. This stream be B and this stream be C. ठीक है. So applying overall balance. Okay. So 1000 is equal to B plus C. Okay, 1000 equal to B plus C. ठीक है. This is the overall balance. ठीक है. Suppose I will mark it 1. Okay, now component balance, that is component here is Na2CO3. So we will do Na2CO3 balance. Okay, so in the feed Na2CO3 0.2 into 1000 is equal to, now here we have Na2CO3.10H2O, but we require mole fraction of Na2CO3, only this. So this molecular weight of this 106 divided by total molecular weight, that is 106 plus 18, that will be the mole fraction of Na2CO3 in the B stream. Okay, so that is 8 plus 6 14 124. Okay, so 106 divided by 124 into B plus the 0.021 C, because it is written the solubility of Na2CO3. The solubility of Na2CO3 at T degree Celsius 2.1%, and that T degree will come in the C stream. The same temperature will come in the C stream. Okay, so from equation 1 we'll find out the value of C and we'll put in the second equation. So 200 is equal to 106 divided by 124, that is 0.855 B plus 0.021 C 1000 minus B, because we have to calculate B. Okay, 200 is equal to 0.855 B plus, oh sorry, this C will not come because we have put the value of C to 021 into 1000 0.021 B. Okay, so here from here we will, if we will calculate, we will get B 214.63 and percentage B upon 1000 into 100. Okay, so this will be the final answer, 21.4%. Okay, so this is straightforward. Okay, switching over to the next question. 1000 kg per hour of thermic fluid to be used as a heat transfer medium is being indirectly heated in a heater from 380 Kelvin to 550 Kelvin. Calculate the heat load on the heater in kilowatt. Also estimate the mean heat capacity of the thermic fluid over a temperature range of interest. Heat capacity equation for the thermic fluid is Okay, so this is straightforward question. Just write in the formula. We have Q is equal to mCp delta T. Okay, if we have a function Cp as a function of T, then mCp dt, right? This is the straightforward question. So m is 1000 kg per hour integration 1.436 plus 00218 t dt, right? And this is 380 Kelvin to 550 Kelvin, right? So 1000, okay, see, kg per hour, Cp is in kilojoule per kg per hour. Okay, so kg will cancel out and dt will cut the Kelvin, so only kilojoule will remain. So 1000 1.436 plus 0.00218 t dt. Okay, I'll not write the limit. So 1000 1.436 550 minus 380 plus 0.0218 0.002 0.00218 t square by 2 divide. So 5 minus 3 square. Okay, so it will give around so the answer will be 4.16.45 into 1000 kilojoule. Okay, so 41645 9. So answer will be 416,449 kilojoule. Okay, if you want to calculate the mean heat, then mean heat capacity is equal to Cp mean is equal to Cp divided by del T. Cp dt divided by del T. Okay, so Cp dt divided by del T. Del T will be 550 minus 380. Okay, and the whole term will come. Which whole term? This 1.436 550 minus 380 plus 0.00218 by 2 550 square minus 380 square. Okay, this whole term will. Okay, so this will give the mean heat capacity. So that is 416.45 divided by 550 minus 380. 2.45. So, 2.45. 2.45. Okay. Kilojoule per kg. Mean heat capacity. Okay. So switching over to the next question. The wall of a cold storage unit comprises a brick layer, thickness this 0.1 meter, thermoconductivity this, an inner layer, polyurethane foams 0.05 meter, thermoconductivity 0.015 meter. Assume one-dimensional heat transfer by the conduction through the composite wall, and that the inner surface of the polyurethane there is at a temperature Tc, outer surface brick layer is temperature Th. Calculate the rate of heat generation. So it is forward question. So in case of heat transfer through composite wall, Q upon A is equal to del T L upon K A plus L upon K B, right? So Q we have to calculate, area we have 260 meter square, del T is 40 minus 10, 50 divided by L upon K, 0.1 by 1.4 plus 0.05 divided by 0.015. Okay, so this will give the Q. Okay, in it will give watt. It will give watt. Okay, Q is in watt. So this is straightforward question. Okay, and carbon dioxide issuing out of a fermenter contains 0.01 mole fraction of ethanol. Okay, for absorption always remember first make an absorption tower, otherwise the question will be difficult to understand. So this is gas in, gas out, liquid in and liquid out. Okay, so very first thing, carbon dioxide CO2 is the gas and entering mole fraction, it is given mole fraction, yani ki that means capital Y2 0.01, which has to be reduced to 2.001 0.0001. Scrubbing with a water countercurrent pack tower, the gas flow rate is what gas flow rate? Okay, 227.3 kilomole per hour. It is not saying combined or individual. Okay, let us assume gas flow rate combined. Maybe assumed constant. Okay, it is maybe assume constant throughout the. It is written maybe assume constant throughout the tower. That means the mole flow rate of mole fraction will not be there. Okay, this is independent. Equilibrium mole fraction of ethanol in gas phase related to this relation. Okay, 1.07x. Okay, determine the minimum liquid rate needed. Number of the overall gas side transfer units needed at 1.5 times the minimum liquid rate. Okay, so x2 is equal to 0. Okay, fine, straightforward question, just formula. The very first thing, sorry what happened? Yeah, very first thing we will see, very first applying component balance. The basic equation G y1 minus y2 L x2 minus x1. Okay, so sorry, x1 minus x2, x1 minus, oh sorry, x1 will be more x2, x1 x1 minus x2. Okay, x1 minus x2. So gs is 227.3, y1 0.01 minus 0.0001 is equal to l okay, I'll tell you, l x1 minus x2. Now always remember, l is equal to l minimum when x is taken from equilibrium relation. So here equilibrium relation is y 1.07x. Okay, so if I'll say x2 is 0 because it is pure written, entering the assumed free from the ethanol. Okay, so y1 is equal to 1.07x1. So y1 is 0.01 is equal to x1. So L minimum will be 227.3.01 minus 0.0001 is equal to L minimum 0.01 1.07. So L minimum will be, let's calculate, 0.01 minus 0.001, I'm sorry, 0.01 minus 0.0001 into 227.3 into 1.07 divided by 0.01, 240.77, 240.77, same unit as GS. And now here what is written, actual liquid rate is 1.5 times the minimum. Actual liquid rate, what actually is going, 1.5 times the minimum. So we'll see, okay, so actual rate is ls is equal to 1.5 times the L minimum. L minimum we just have calculated, so we'll multiply 1.5, so we'll get 361.2, I can write, kilomole per hour. Okay, now what it is saying, number of overall gas side transfer unit. Okay, so very first we will see the absorption factor. What absorption factor is saying, ls upon gs upon m. ls is 361.2, gs is 227.3 and 1.07. 227.3 and 1.07 is m. So it will give divided by 227.3 divided by 1.07. So 1.458. So it is a much higher value, 1.458, which is much higher than 1. Okay, so NTU of gas transfer, that will be ln y1 minus mx2, y2 minus mx2, 1 minus 1 upon a plus 1 upon a, 1 minus 1 upon a. Remember, if you will calculate NTU, sorry, number of plates, KBS formula, number of plate, then this portion will 1 by a will be replaced by ln a. Okay, so this is the overall change. So we'll put the value ln y1 is 0.01 minus 0, y2 0.0001, 1 minus 1 upon 1.458, 1 upon 1.458, upon 1 minus 1 upon 1.458. Let's see what will be the value of NTUOG. So if I do reciprocal minus plus 1 into 0.01 divided by 0.000 plus 1 divided by ln. Memory save. Around 11 plates. I think the answer is not correct. I think what I have remember, maybe I have done some calculation mistake. So this is the formula and just check the answer. Okay, 11. So switching over to the next question, steady state plug flow reactor PFR data for isothermal, and this will be isothermal irreversible reaction A that is B is shown in the table. Reactor space time was 10 seconds in both the cases. Okay, so tau is same for both the cases. Other things such as feed and the product density. So volume is not changing, liquid phase reaction is happening in the system. Reactor temperature and same in both the cases. Okay, temperature is same. So if the reaction is known to be non-zero integer order, find the reaction order and the rate constant. Okay, so very first we write the rate equation. Rate equation means for nth order reaction minus r equal to kc to the power n. Okay, now performance equation of PFR, we know that when we will put the value of minus ra as kcan and then we will integrate it, and then we will see that we have this expression. Okay, this expression, we will come this expression. Now our job is to find out the order and rate constant. So suppose if I take n is equal to 1, okay, then this equation reduces to some value something, then I will find k in case 1 and k in case 2. When k in case 1 will be equal to k in case 2, that will be our order. For first order reaction, if you will put n equal to 1, if you will put here, if you will put n equal to 1, k1 will not be equal to k2. For n equal to 2 as well, k1 will not be equal to k2. For n equal to 3, k1 will be equal to k2. So our order will be 3. Okay, so do it yourself. It is very straightforward question, very easy. Okay, switching over to the next question. A particular metal react with a certain liquid and the product passes into solution. Three non-porous solid sphere of same metal and of diameters 10, 20, 30 mm respectively were placed in a very large stirred pool of the reactive liquid at the same time. After an hour, it was found that the pool had only two spheres, diameter 10 and 20. That means 30 mm sphere is completely dissolved. After another hour, and the pool has only one sphere 10. That means after 2 hours, 20 mm sphere dissolved, and after 3 hours, 10 mm also dissolved. Okay. Explain these observations through appropriate derivation using a more likely rate controlling step out of the. Okay, so first, for film mass transfer, the rate of dissolution is controlled by the diffusion of the solute. Okay, we will assume that the film mass transfer coefficient will be rate limiting. So mass of the sphere will be density into volume of sphere pi by 6 d cube. Rate of mass loss dmy by dt, that is minus k is the mass transfer coefficient, area into del c. Okay, we'll put the value of area pi d square. Okay, this is equation 2. Again, from equation 1, if we integrate this dm by dt, density into volume, then it will give dt by dt. dm by dt equal to rho pi by 2 d square dt by dd by dt from 1. Okay, so this will be equation 3. Now equating 2 and 3, you will get this. Okay, solving this whole 2k del C upon density is a constant term. Okay, will not changing. So it will give dt is equal to d naught minus alpha t. Now it is showing that diameter is a linear relationship, showing linear relationship with time. Diameter of the sphere at any time t showing the linear relationship with time, right? And it is in decreasing order. If you plot the graph, you will see that the slope is decreasing. That means and here in the question it is saying that the more diameter of the 30 mm diameter is dissolving first, but here from this expression it is completely reverse, showing reverse result. Okay, so same result will come with the surface reactions. Okay, so same result will come with the surface reaction. And here minus k dash is the reaction constant. There k will was the mass transfer coefficient. Here k dash is the reaction constant. So we will get the same result here. Okay, so it is difficult to say whether the surface is rate controlling or reaction mass transfer rate is controlling, but this was the subjective question, so you have to write your explanation. A mixture of A and B conforms closely to Rohr's law. So they are following Rohr's law. Pure component vapor pressure is given. If bubble point of a certain mixture A be 76 degrees Celsius at a pressure of 80 kilopascal, total pressure, find the composition of first vapor that forms. Okay. So for component 1, Rohl's law, we will write partial pressure in terms of mole fraction to total pressure equal to XA, P is at, where YA is the mole fraction of the vapor phase, XA is the mole fraction of liquid phase. Similarly for component 2, adding 1 and 2, we will get this YA plus YB equal to 1. So we will get this ultimately. Okay, so PT is equal to XA is equal to 1 minus XP, because XA plus XB is equal to 1. So putting the values of pressure after calculating from the Antoine equation. So XB is equal to 0.139, XA equal to 0.86. Now putting this value here, XA, we have PA set, we have PT. So we will get YA. Okay, so this is the final answer. Okay, so switching over to the next question. The reaction N2 plus O2, that gives 2NO, takes place in a gas phase reaction 2700 degrees Celsius and 2025 kilopascal pressure. The reaction mixture initially comprises 15 more percent oxygen, 77 more percent nitrogen, and rest inert. That means 8% inert. 15 plus 77, 7 5 12, 7 8 9 90, 8% inert. The standard gives me energy change for the reaction 113.83 kilojoule per mole. At this temperature, ideal gas behavior, assume calculate the partial pressure of all species at equilibrium. Okay, so very first we have the reaction N2 plus O2, that is 2N, right? E is the extent of the reaction at T equal to 0. At T equal to 0, this is 0. At T equal to 0, no product will form. So feed is 0.15 O2, 0.77 N2, and 0.08 inert, and the same quantity we will get here at the end of the reaction, 0.08. Okay, now E is the extent of reaction, NO formed, 2E, right? Then O2 reacted. O2 reacted will be stoichiometric coefficient of O2, stoichiometric coefficient of NO into 2E. So E is the O2 reacted. So O2 unreacted, feed minus O2 reacted will be O2 unreacted. So this is O2 unreacted. Similarly, N2 unreacted. Now, total number of moles after reaction completion. So N2 moles after reaction, O2 moles after reaction, NO after reaction, inert after reaction. So this plus this will give 1, and 2E minus E cancel out 2. So total moles will be 1, remain same. Now we know that Kp equal to Ky P summation of nu. So summation of nu is the stoichiometric coefficient. Positive for product, negative for reactant. So 2 for NO, 1 for O2, 1 for N2 is equal to 0. Now mole fractions. Mole fraction is, we know that number of moles divided by the total moles. Total moles we just have calculated this. This is the total moles. Okay. So 2 is the mole at the end of the reaction. NO, N2, O2, and inert. Inert will not change. It will remain same. Now Ky is 2E for product upon the reactant. So 2 we have product only 2e. So 2e and square will come for the stoichiometric coefficient because it has stoichiometric coefficient 2. So square will come divided by N2O2. So we will get this. What is K? Kp is this. So see, this kilojoule and kilojoule will cancel out. Kelvin, Kelvin will cancel out. Mole will cancel out. This K will remain same. And remember, K is a number. That is 1000. We write now 12K, 13K. This K is a number. Okay. So this is the Kp. So put this value Kp. Put all the value here. Kp. This term will be not in the final calculation because p to the power 0 is equal to 1. So Kp is equal to Ky. So Kp we have, Ky we have, Ky is this. We will calculate E. We will put all the values of E here, here, and here. We will get the mole fraction. We have to calculate the partial pressure. So partial pressure is equal to mole fraction of a component into total pressure. Total pressure we have 2025. Partial pressure we have to calculate. Mole fraction we will calculate. Okay. So this is straightforward question. So this is a straightforward question. Every year GATE asks this type of question. This question is very easy. I will not do here. This is for you guys. Okay. So capital cost of a pipeline of exotic material is estimated as 3 into T 1.5 rupees per M is the year, where D is the pipe diameter in mm. The annual maintenance cost is estimated to be 10% of the total capital cost. Annual operating cost of the pipeline is given like this. Annual operating cost is this. Okay. So estimate the most economic pipe diameter based on the least annual cost. We have to minimize the annual cost. Nearest multiple of 10. Okay. 10. Okay. So total annual cost will be, since 3D 1.5 RS per year. So this will divided by 10 because the amortization period is 10 year. Okay. So, and 10% is the maintenance cost of the total cost. So this plus this divided by the 10 years because it is annual operating cost asking. So divided by 10. So ultimately we will get this expression, and after when you will solve, you will get 220 mm diameter. That is optimized dia. Okay. So guys, we have completed the 1998. Okay, and we will complete uh, so guys, we have completed the 1998 and we will start 1999 very soon. So take care guys. Please like, share and subscribe because it requires a lot of effort and time to make videos for you. And since I'm also lacking with my work as well, so just share it guys, and share among your friends. Okay, bye guys, take care.